I hope you guys are still enjoy this course.
Of course.
I mean, we didn't do attendance count, so
That's great.
I hope you guys are very interested in photovoltaics. So we talked about thin film photovoltaic last week. Amorphous silicon started very hot, very promising, and at the end, the stability issue eventually ended the life of that material, that candidate. And today we are talking about more realistic, I mean the currently commercially available thin film technology. I think it's only one that is competitive and can be a competitive candidates in the photovoltaic industry. Although 95% are silicon-based, but we have another candidate, thin film technology, that is taking a certain market share and still competing with other candidates, other technologies. All right, so we come back to the same story. This is the reason we talk about solar spectrum all the time, I mean from very earlier time, is because we use that a lot to make sense of many things. And we talk about how solar cell absorbs photons, and we still use silicon as an example. This is where the band gap of silicon is, right? About 1.1 eV and 1100 nanometer. So the photons with energy higher than that will be absorbed, will contribute to the output current. And the band gap not only does that, to allow you to absorb certain part of the solar spectrum in this blue area, it also determines how big a voltage you can output. You can imagine the higher the band gap, the higher the voltage. It's like the ping pong table. If the table is higher, the potential difference will be higher, right? You output higher voltage from your solar cell. So the voltage times current give you the power, right? So the output from solar cell, it's the power that matters. And it's the power that determines the efficiency. Because the efficiency is the output power divided by the input power. So that's efficiency. Efficiency is the whole solar spectrum. You count all of them, the total power that comes down to your solar cell. And then the output power is the voltage times the total current. All right. So the voltage decreases when the band gap decreases. So therefore, a natural question would be, what is the best band gap that can give us higher, or the highest possible efficiency? Silicon is certainly not the best candidate because the conclusion is the band gap is too small. So what is the best candidate? What is the best possible band gap that can give you the highest efficiency? So from this chart, or from that Excel file you guys did the first assignment with, you can actually do that calculation. Let's say band gap minus half a volt will roughly be the output voltage. So 1.1 EV will give you 1.1 minus 0.5 volt. So probably the voltage will be around 0.6. and the 0.6 times the total current that you can possibly get. That is another question in your assignments, right? So that is the total power. 0.6 volts times the 44 milliamp per square centimeter, if you remember that correct answer, is the total output power. If you do this math on your spreadsheet, by doing that for different band gap, you yourself can do a calculation, plot something, find the maximum power output. So what it looks like is this. It's going to be this curve. You can do that yourself. So when you have, so this is band gap, okay? Higher energy on this side, lower energy. So silicon is here, 1.1 eV. And you can see this curve when the band gap is very small, somewhere here, germanium is 0.6. So when you have small band gap, although you can absorb more photons, but because the voltage is too low, the total power is not very high, therefore you have lower efficiency. So when you increase band gap, you're gradually reaching the highest possible efficiency. And then when you have too high a band gap, you start to lose too much photons. You only absorb a small section of the solar spectrum. Therefore, your output power also decreased. So that is something you can do that. And then we can see around 1.3, 1.4 is probably the best band gap that you can get highest possible efficiency. So that is a theoretical analysis that scientists did that maybe in 1950s, because this is easy to do. I mean, even you can do it today with your data file. And in 1950 or before 1970s, we know, I mean, the scientists knew the renewable energy has potential applications. At that time was mostly military and space applications, but ever since the first energy crisis, 1973, even the government start to pay more attention on alternative energy sources. So there has been an effort ever since to look for alternative energy sources, and this question naturally become a very important question to the scientists. So in 1960s, 70s, silicon wasn't cheap at that time. I mean, the IC industry didn't actually start it yet. Therefore, making single crystal silicon was not cheap. Therefore, when they were thinking about that question, the cost wasn't a big issue yet. I mean, they're all expensive no matter what. So therefore, from the very beginning, they would like to find the best candidate possible. Okay, so one thing that was already studied was the band gap for a semiconductor. There were some well-established method to measure the band gap for each semiconductor materials. So along that curve, you see germanium, silicon, gallium arsenide near the top, cadmium telluride near the top, and the copper indium selenide, and the copper gallium selenide. And of course, you can have other things. there are many others along, you can mark on the curve. But near the top of the curve, there were several potential good candidates. Naturally, scientists would try to study those materials. I mean, you have a right band gap, you also have to develop a right process technologies, right? You have to make them into a solar cell, and you have to find a cost-effective way of making them into solar cells. Okay, so that was the reason there were studies on on those materials. Gallium arsenide, of course, was a candidate for very high efficiency solar cells because it is a 3-5 semiconductor. It's a direct bandgap material. So we talk about direct bandgap materials. Do you guys remember what's the benefit of a direct bandgap semiconductor?
I think it absorbs better, I think, if I remember correctly.
Direct bandgap versus indirect bandgap, which silicon is a indirect bandgap. So the difference is direct bandgap, you have very high absorption coefficient, meaning you need much less material to absorb same amount of photons from the sun. Silicon requires millimeter thick to absorb all the photons. Well, gallium arsenide require only half a micron, so it's like 1,000 times thinner. However, gallium arsenide is a expensive material. I mean, material expensive to fabricate. It's more difficult than silicon to make a single crystal. So gallium arsenide and its derivatives, meaning you mix with other contents, can only be cost effective to be made into very high efficiency solar cells used in the space application. So for terrestrial application, people are looking for cheaper methods. So that there are two candidates. One is the cadmium telluride. The other is the mixed compound between copper indium selenide and the copper gallium selenide. These two compounds can be mixed with continuous concentration. You can vary the gallium versus indium at any composition, still maintain the single crystal property. And so we will talk about these two compounds in a little bit more details. First of all, cadmium telluride, okay, from the crystal structure, you can see that this is still a similar diamond crystal structure or tetrahedral structure, similar to silicon. And it is a binary compound. Yeah. So the binary compound has a much bigger advantage versus others, more complex compound. That is easier to control the composition, right? Instead of, for example, copper, indium, gallium, selenide. This is a quaternary compound, meaning you can have phase separation, because some part want to be the copper indium selenide, the other wants to be copper gallium selenide. They want to separate. So in order to prevent that kind of phase separation, you have to do something more precise control in the process. Therefore, it's difficult. So for binary compound, you don't have to worry about that. Whatever you do, it ended up only cadmium telluride. There's no other choices. So that made the process much simpler. And but why copper indium gallium selenide still be a good candidate? Because if you look at the band gap versus lattice constant, and on the very left is copper gallium selenide here, and the copper indium selenide is here. So by mixing them, you can vary the band gap to any value you want. So that gives the engineer and the scientist a freedom of changing the band gap. Yeah, cadmium telluride, you can only have one band gap. There's no other choices. But this second, you can mix them in any way you want. Therefore, you can fine-tune the band gap. So that feature is very attractive. So therefore, there was a huge amount of effort put into that. So these two technologies was developed almost like started at the same time and moving side by side in parallel. And the quality and the efficiency of the cell was also moving shoulder to shoulder. They are roughly in the same ballpark. But now when we enter 21st century, when the renewable energy becomes almost like commodity, also due to the concern of environmental protection, global warming, and safety to public, the question of cadmium-based material become a big issue now. When we look at cadmium telluride, the cadmium is a toxic material. It's carcinogenic element. So last century, the cadmium-based chemicals and the products was banned in Europe. Wasn't in the United States, but in Europe they were not allowed cadmium-based product to be manufactured, including nickel cadmium battery at that time, that little thing, if you remember. And so they argued that this is carcinogenic material. Why do we allow them to be ended up in the landfill? I mean, when they install solar panel, no matter how long the lifetime is, they eventually will become a garbage, become a trash when they reach the end of their life. So therefore, how are we going to do with it? So that was the first question. And so the answer for that is, we will talk about the company later on. The answer for that is the solar cell manufacturer promised to recycle them. I mean, to buy them back actually, not buy them back for free. I mean, take them back for free at the end of their lifetime. So you don't have to worry about putting them in the landfill. So that actually, at the end, the European Union stopped, terminated that ban for cadmium. And these two candidates are all direct band gap materials. So therefore, they have all the benefit of using less material to absorb more photons from the sun. And the cadmium telluride, although it's carcinogenic, but it's very simple, Therefore, the band gap is very close to optimum. So therefore, they can be fabricated with very high consistency and lower cost. And on the other hand, this CIGS, it's a ternary compound, or can be quaternary compound if you add selenium to replace part of the sulfur. So therefore, it's become quaternary or even more complicated. And to control the composition, although it's a two-sided sword, it's give you the freedom of changing the band gap, but also increase the complexity in the process engineering part. And so that is could be the fatal problem eventually, although it's not finished yet. Okay. Well, we talked about all the benefit from cadmium telluride and the CIGS. And the one thing that is not, when you have a very good band gap for this material, for these two materials actually, but they are not like silicon is the group 4 semiconductors. So they are like 2,6. Cadmium telluride is 2,6 semiconductors. So this kind of semiconductors, they have one problem. That is, you can dope this material into one type of semiconductor, but not the other. Meaning, easy to make it into P-type, very difficult to make it into N-type. Right? So therefore, it's not like silicon, you can dope into both types, you can make it N and P, and you can make a so-called homojunction, PN junction. And in the case of cadmium telluride and CIGS, you can easily make into P-type, but not N-type. So then what to do? In order to finish a PN junction, and this kind of technology went through a difficult technology development, and eventually came out almost like a technical miracle in that case. That is a very special method of making the N-type counterpart. It's called the cadmium sulfide. Cadmium sulfide is a, you see, cadmium sulfide is similar to cadmium telluride, right? Cadmium telluride, you can make it P-type, and the cadmium sulfide is a N-type material. And it's a naturally N-type material, and it can be made by a method called the chemical bath deposition. And just because there was a method like this, which enabled this technology to move forward. This is almost like a miracle. Otherwise, this kind of solar cell will not even be a competitor in the industry. So chemical bath deposition, simply put, is a like a water-based solution in the container. I mean, you heat it up to 80 degrees, not even boiling, and then that reaction will happen in the liquid phase. You put your solar cell into it, and it will naturally coat one very good quality, high quality layer of cadmium sulfide on everywhere that you put in there. And that actually becomes a very high quality N-type material to work with your P-type cadmium telluride or CIGS. And that low-cost, high-quality cat sulfide enables all this technology to become a good competitor in the solar cell industry. Otherwise, these two kind of solar cell will never actually exist. I mean, just because this technical miracle that happened. So when we look at the that efficiency chart, see here this yellow filled circle is cadmium telluride. Its solid green is CIGS. So these two actually move side by side. You see sometimes this candidate is higher, sometimes the other is higher. And only in the for quite a long period of time from 1990, 94, and until 2014. It's like 20 years, right? CIGS had higher efficiency. But in 2014 and onwards, and cadmium telluride surpassed that, become a higher efficiency. So this was all because the industry, what happened in the industry. Yeah. So we are going to talk about this company who made this cadmium telluride solar cell a real competitor and actually succeeded in the industry. So this table summarized, listed major technical specifications and also some other informations regarding the manufacturers. So the CIGS, one thing I didn't mention was CIGS. The reason CIGS still exists was because it avoided the toxic cadmium in the cadmium telluride candidates. People can constantly arguing about how bad the cadmium is to the environment. And then they were saying copper union gallium selenide doesn't have that problem and doesn't have the supply chain issue because the tellurium is a rare element on Earth. So when this candidate become mass produced, they are constantly running into the supply chain problems. So therefore, people are arguing that CIGS will eventually replace cadmium telluride. And for the 20 years, they were higher efficiency in the record and made it a stronger argument that we should continue invest in this technology. And so for now, there are much less companies working on the CIGS than maybe 20 years ago. 20 years ago, there were so many more different companies trying to develop this technology. We saw many companies eventually went bankrupt primarily because they couldn't solve the problem with that quaternary compound. They, in the process of mass production, you can make a small area sample with a perfect structure, but when you do mass production, when you do the large area, there are always some problems showing up. And they can all trace back to that quaternary compound, which was the root cause for those problems. Yeah. And here are the band gap. Well, this is a nice picture. Worth mentioning that this is what I said, a P-type cadmium telluride, and this yellow is the cadmium sulfide. This too works very nicely. They are not so-called homo junction because they are not used. They didn't use the same material like silicon. Therefore, they have different band gaps. Cadmium sulfide has a 2.4 eV, and cad telluride has 1.5 eV. So this is called a heterojunction semiconductor device. So you see this bigger band gap normally would incur a barrier for electron transportation. But just happened in this case, in the solar cell operation, this barrier is on the valence band side. And the holes created by photons doesn't come to this direction. Holes goes to the P side, on the right, electrons coming to this side. So therefore, electrons doesn't have a barrier. So this is another technology miracle for this to happen. This material just happens to be perfect for this device structure. So therefore, we rely on a lot of technical miracles for this to happen. I don't dive into details here. If you, in the future, you happens to be working on this type of solar cell, you will certainly appreciate all these technical merit of these candidates. And in 1950s or 60s, 70s, we have the candidates with a perfect band gap, and already we have several miracles like cadmium sulfide to work with it. And people also found that with this kind of material systems, you can use many different ways of depositing this material on a large sheet of glass with very high efficiency and very low cost. You see, the cadmium chemical glass deposition is one low-cost, low-temperature method, and this physical vapor deposition. If you guys are familiar with that evaporator, actually, you can just evaporate the material onto the sheet of glass, and then you are done. And this thing doesn't, like crystal silicon, you have to make that single crystal ingots in the crucible for days before you can harvest wafers. And you can even use the method called spray paralysis. Like you use spray gun when you paint your wall. Spray pyrolysis is you can heat your glass and then spray the materials on, and naturally will form a nice coating. So these are the benefit for this material. You can do that with many different ways. And here is the schematic showing how easy you can do the chemical dust deposition. So in that, this is a lab setup. You have a beaker, you put it on the hot plate, and you heat the water to 80 degrees or 90 degrees, and you mix this chemicals called thiourea plus ammonia chloride. And this reaction will happen, cadmium will deposited on the glass substrate, give you the cap sulfide. And so this is the reason why it is so cheap. It doesn't need so much high expensive equipment. You can do that with very easy setup. Of course, to do that in the large scale, you still need some engineering, of course. But the fundamental thing is just very simple. And this is a schematic showing how you can scale it up. So this reaction doesn't continue forever, but will get worse when you pass the best quality period. For example, first 1 minute, you get a high quality cap sulfide. After that, you are going to grow some particles in the liquid phase. You grow something in the liquid phase, therefore the quality of the film will degrade. And to mitigate that, you can add some filtering system to continue the chemical reaction. So by doing that, you can use the liquid source chemicals for a longer time, and better use the source material that way. And to deposit cadmium telluride, we talk about it's pretty much a thermal evaporation process. So this is a lab setup called closed space sublimation. Do you guys know what sublimation is?
Yes.
Okay, what is it?
Liquid to gas, or sorry, solid to gas.
Right. Yeah. Cadmium telluride don't easily turn into liquid, especially in the vacuum case. So because the pressure is so low, they just sublimate. And one way to purify this material is to sublimate once from one substrate to the other. You left impurity behind. And if you do that several times, you can get purer and purer material. But in the lab, you normally buy a source material, telluride, with maybe 5 nines or 3 nines. You do this sublimation once, you get much purer material. So that is the material you can use to make solar cells. So this is the SEM pictures. Did you guys ever see that kind of pictures? SEM?
Mm-hmm.
Yeah, so this is how nice a little polycrystalline you can get. I use that method. Another technical miracle. I probably just need to mention it. No need to dive into details. It was that both cadmium telluride and the CIGS, they are perfect. They have perfect band gap for solar applications. However, the processing technology wasn't as easy as the other candidates like silicon or amorphous silicon. So the problem with the cadmium telluride was on the backside. When you are trying to put the metal contact on the backside, they don't adhere very well. And what they actually found was you have to use copper as the back contact. Copper is an infamous material in the semiconductor industry. Because both gold, silver, and copper, they are in the same column. They are infamous because they diffuse very fast. So gold, silver, and copper, if you put them in any device, they try to diffuse in all the directions, and maybe you can make a device working very well this week, and maybe after the 1 month you leave it in the sample box, the copper just diffused long distance without notice, and then the device actually won't work. And so therefore, gold, copper, and silver, they are very often considered as contaminants in the semiconductor industry. So therefore, it's very strange that the industry found copper is needed in the back contact. And how to make it to work? And I actually showed one figure here. So on the back side, if you have to do copper, the copper will diffuse all the way to the front. And therefore, they have to implement something in the front to prevent copper from shorting the p-n junctions. So they have to make this front contact layer as a barrier to stop copper diffusion. You see here. So when the industry found that copper is the only candidate to make that contact, then they have to implement something else to mitigate the diffusion problem. The copper diffused all the way from the back to the front, and this front contact layer, they have to make them like bi-layer structure. So one layer is used to stop copper diffusion. Anyway, another technical miracle that it actually worked. For other solar system, photovoltaic devices, this is almost like, no way. How can we make it work? There's so many problems. But that's how things happened for this candidates. They are carcinogenic, they are toxic, they are expensive, they don't have so much on Earth, therefore there will be a supply problem, and it's difficult to make them into a working device, but they found the perfect band gap is so attractive. So they tried every possible way to make it work. So therefore, this cadmium chloride treatment also become one of the major process that you have to do in order to make the whole thing working. They are actually doing that with oxygen in there, and to actually oxidize the tellurium a little bit. So who would have thought about doing that? Because in the semiconductor device, we normally don't want oxygen in there. Oxygen will normally do something bad. But in this case, they form something, tellurium oxychloride, and that is necessary to make a so-called OV contact, meaning there's no barrier on the backside metal and the telluride material. So all of these technical approach sounds ridiculous when you just thought about it. But that was the only way that can make it work. So this is about copper doping on the backside, showing how this copper is detected in that measurements, and that actually made this backside contact more of an only contact like this, rather than like that. All right. So you guys probably more interested in how this cadmium telluride become commercialized. So we have to attribute the success of cadmium telluride to this guy. So this guy, Harold McMaster, was a kind of a legendary figure. He was kind of he was an expert on glass. I think he based in Ohio, Toledo, Ohio, I think. His first business was around the glass industry. He was the first one to think about to build a solar cell manufacturing facility next to a glass factory. Yeah, because to make a large area solar panel, you need to use glass, right? And before that, people are buying glass from the manufacturer. They come in with trucks and a sheet of glass in a big crate, and then they have to wash the glass and put down metal contact, TCO, whatever. So he was the first one to thought about, okay, why don't we build the solar factory next to the glass factory? So the glass was made out of that process that can be directly moved into the solar manufacturer facility without packing and cleaning, because that will save a lot of cost, right? You don't have to contaminate the glass and then clean it. So that was the first thing he was trying to do. And so 1984, if you remember, we talked about amorphous silicon last week. He was the first group of business people who was trying to catch the bus. 1984, he founded Glass Tech Solar, using amorphous silicon, of course. And if you remember, that kind of business was pretty much grow very quickly, and then the bubble get burst also very quickly. So 1984, he founded Glass Tech Solar, and then six years later, so 1990, he kind of gave it up. It doesn't work. But he gave up amorphous silicon, but he didn't give up solar. So he was thinking, what else can we do? I mean, he still want to make that concept of building solar facility next to the glass factory. So then he said, okay, why don't we try cadmium telluride? Because the cadmium telluride has such a potential. And at that time, if you remember, the European Union was banning the cadmium. Only the United States is allowed to do research or manufacturing. So he was, okay, he wants to try cadmium telluride, but how can we do that at very low cost was his major objectives. Okay, so it is good that someone isn't so familiar with cadmium telluride. If your mind is kind of restricted with the the process I just mentioned, sublimation and cadmium chemical bath deposition, that kind of technology used in the laboratory, you might never come out of it, think out of the box, find something unique and different. So he wasn't really a semiconductor guy, so probably that helps for him to find a better way to do this. And by the way, he was an entrepreneur, over 100 patents, and he was not only interested in solar cell, he was a glass genius, like I said. He was very familiar with glass industry, and he even had his own design of kind of engine, a master rotary engine. I don't know what it was. Maybe you guys can Google it. So he founded, he started working on cadmium telluride in 1990, and then through about 9 years, they had some preliminary research R&D going on. And I actually visited his factory in 1999, about 2000, year 2000, I went there. And they are like pilot production line for 1 square foot, small size. And but the major event happened in 1999 was that they had a investor from Walton family, the Walmart Walton family. So one of the son of Walton family, John Walton, invested I don't know how many $1 million, and then they changed their name to First Solar. And that name, I was asking, why do you call yourself First Solar? They said, no. I mean, it kind of vaguely answered my question, saying that they were thinking they are the first company who can mass produce large area solar cells. So after that, after Walton family's investment, their technology actually evolved and progressed very quickly. And by the time, another 10 years after 1999, and they lower the cost of solar cell below $1 barrier. So 1 watt, 1 peak watt cost less than $1. So that is one of the major milestones. Because at that time, most of the solar cell manufacturer can only make solar cell with like $2 or $3 per watt. But they lower that to less than $1. And the interesting to learn that they achieved that not by like doing scientific research. I'm not saying they didn't do research. They rely on a technology that is kind of a brutal force. And why I'm saying it's a brutal force, they are not doing research like we understand the physics first, understand how the electron jumps and falls, and they are doing statistics. For example, there are like 20 parameters in the manufacturing process, and they just turn the knobs one after another, it's called a design of experiment. You have 20 factors, 20 variables that you can change, then you can design a big matrix. It's like pharmaceutical company, they do that as well. When you have 20 components, you don't know what composition you want, they also do that. By varying the composition, and to see the effect. So they did that way before they fully understand the physics. So they did that in probably 9 or 10 years. And then they eventually came up with a process that can lower the cost to $1 or less. And in 2013, they further lowered that to 68 cents per watt. And so this number was, even at that time, was the lowest possible cost in the whole world. I mean, that was a big news and very happy, very good news to DOE, because the DOE, I will talk about the Sunshot. I actually mentioned that. Sunshot initiative, they want to lower the cost of photovoltaic to a certain value in a certain year. And First Solar actually led that trend. And if you remember, this was a factory in the United States, not a factory in Asia or China, something like a low labor cost region. So for that reason, this was amazing. So much lower than what people would expect. And another interesting thing was when they announced their achievements, lower the cost to $1, and the GE found, oh, this is interesting. So they want to take a cut on the market if they are like a future of renewable energy. So GE very quickly put together a research team, and they also did similar research, and they actually made some record-breaking samples and get recorded in that NREL's chat. And that put a kind of threat to the First Solar. First Solar thought, wow, GE has such a deep pocket. I mean, if they commercialize their technology, it's going to be a big threat to us. So they decided, okay, we cannot allow that to happen. Therefore, they negotiated, and they actually spent some money to purchase GE's solar department. And so they bought that department with 1.8% of the company's stock. And therefore, their technology strength also increased because of that. And that from 2013 to 2016 was the like honeymoon period of time, when that record efficiency was broken many times, and from 16% to over 22% in a short few years. And at the same time, the First Solar, they were leading in the world market thin film technology solar cells. So because I talked about that before, since the China invested so much on solar industry since the financial meltdown in 2008, and most of the American companies actually went bankrupt, and they couldn't afford to make anything that competitive on the cost. But First Solar was the only company that can make the solar cell cheap enough to to be competitive. And of course, they survived that competition and continue to be the leading manufacturer in the United States. And I think I mentioned somewhere in 2011, European eventually agreed to allow cadmium-based solar cell to be sold in Europe. And of course, First Solar promised to take the solar panel back after the lifetime is over. So that gives the buyers, customers, peace of mind when they purchase First Solar's solar panels. All right, so what kind of technology Harold McMaster was trying to develop in the mass production mode? And this is a schematic thing, and this is the barrel, heated barrel, and the bottom is a conveyor belt that you have sheet of glass rolling underneath it. And this barrel, there are two feeders from both sides. And you can put in cadmium telluride, or cadmium and tellurium, whichever composition, maybe include some dopants. Put them in the feeder, and then there is you see this mechanism to scoop the material and feed them at certain constant speed. And once they enter this barrel, and they get vaporized, maybe sublimated into the gas, into a mixed gas phase. So vapor projected out like a squirt gun. And this, the gas phase coming out of this thin slit on the bottom, they sprayed on this heated glass panel and immediately condensed on the glass, and at the same time recrystallized on the glass. So this idea was intrinsically very, very cheap, right? You can just move the sheet of glass and get deposited very quickly. But what matters is how well the quality. What is the quality you can expect from this? So they use that statistical method, trying to adjust all the possible knobs they need to adjust on this system to optimize the property. One batch another takes many years to optimize, and that is how they accomplish their manufacturing process. And this technology, of course, later on becomes much bigger. This probably is like schematic for like 1 foot wide pilot production. In the real manufacturing, the glass panel is like 3 or 4 feet wide and very long on the other dimension. And they have to think about not only the cadmium telluride layer, but also the front contact TCO and the back contact copper, and also this cadmium chloride treatment, and anything else. They even replaced that chemical bus deposition with a method similar to this, like a PVD method, vapor deposition method. So in order to commercialize the process, you cannot continue using the laboratory level method. So they continue to do that. And it's highly proprietary. I mean, they won't allow anyone to look at them. in the factory, unless you are working in that department. So that method, they call it the vapor transport deposition, the VTD. So when we attribute their success to Harold McMaster, but we also have to acknowledge the help they received from the solar industry as a overall, right? And you see here, they first would call their company Solar Cell Inc. Before 1990, and they gave up. No, they call it Solar Cell Inc. in 1990 when this first started, and they got a lot of help from National Renewable Energy. I was working at Ecgr from 1996 to 1999, and during that period of time, they get a lot of funding and research support from Ecgr, and then that allowed them to continuously improving their technology. And DOE also gave them support for quite a long time until they actually started to make a profit. I mean, they eventually don't need the support anymore. Yeah, so I just want to mention that. So this technology, if you look at this, that yellow circle is the cadmium telluride. You see, First Solar held that world record until 2013, 2012, and then GE jumps in. GE, they actually get the results, get the record efficiency pretty quickly, and they show their record efficiency, and then First Solar keeps another efficiency, and then at 2016 or so, First Solar bought GE. So now you see this after 2016, they reached like 22.1 here, 22.1 efficiency, and there was no further improvement after that. I think they almost like reached a theoretical limit of that technology, 22.1. So the commercialized solar panel, if you buy from them, you only get something like 14% efficiency. And the 22 was in the laboratory condition, a small sample like 1 square centimeter or 1 square inch at most. So when you scale up, there's always some losses. But if you look at the green circle, that's CIGS, they actually reached 23.4, which is higher than cadmium telluride. But just because CIGS was a quaternary compound, they constantly struggled with the process problem. So therefore, the commercialization of that technology continuously suffer. So there are still several Japanese companies still working on CIGS, and they are not giving up yet. But we will see what happens. Okay, So we are on week 7, and in the next week we will actually conclude the lecture part of this course, and I probably on week 9 I will tell you guys. The initial plan was to measure solar samples, right, in the laboratory, but my laboratory is in the middle of moving from Cameron Hall to Grigg Hall, and right now it's out of the Cameron, but not being in the Grigg Hall yet. So the lab in the Grigg Hall will not be ready anytime soon. So you guys unfortunately will not be able to do this. So I will give you guys a different assignment. I can just confide a little now. It's to design a solar system, rooftop solar system for a house. So you guys need to do some research. Yes, have a question?
No, go ahead.
You guys need to design a rooftop system for a residential house, and considering the annual solar illumination based on your latitude, and based on the weather, and there are data there available. You can see how much sunlight we get in Charlotte area, for example.
Google Solar.
Month after month, January to the summer and then to the winter, you get different amounts, so you need to do that kind of research. So I probably will change the assignment from this measurement to that solar house design. And this week, instead of talking about measuring the solar cell, I will probably talk about how to do that assignments. So that's my plan is, in 2 weeks, we will talk about that. Okay, you guys have any questions?
Yeah, so for the new project, is it going to be more of a focus on calculating the irradiance for a year at a given location, or is it going to be more on designing microinverters versus?
You will have to, first of all, you need to, I give you a task to design maybe a 10 kilowatt hour solar panel, on the rooftop.
Like a
Total
system.
wattage. Okay, once you know that, you will decide what the angle of the roof, and what is the latitude of this location, and what kind of how many solar panels you need to buy, and based on the efficiency, and how many hours of sunlight can you get in average year round, and then what else do you need? Do you need an inverter? You need a battery, or you need a grid connection? So you can do research as to government policy, and a more practical thing you need to.
Do we have any parameters, like an efficiency goal or a number of kilowatts per month, anything like that, or?
Yeah, that is part of your research. You can find out. I probably won't give you too much information if you can find it yourself. I will just ask you, okay, we need a house, rooftop solar system with 10 kilowatt hour power, 10 kilowatt power generation capability. I mean, if you find a lower efficiency panel, you will need a larger area, right? And then the inverter, the connectivity, you will actually figure out how to do that. It's not rocket science.
Not at all.
Since you guys are doing like inverter circuit design, you probably know the work principle. And you just need to Google it.
Do you have a
just-
preference between microinverter versus a single inverter?
Well, that's all up to you, as long
Okay,
as
okay.
works, right? And you
Okay.
need to consider maybe power, how much power that inverter
Dissipate.
can work, can handle. All right, yeah, I just hope